Okay, so example 4 says, for a certain type of computer chip, the proportion of chips that are defective is 0.1. A computer manufacturer receives a shipment of 200 chips. Is it unusual for the proportion of defective chips to be less than 0.075? Now, when they ask that question, they're referencing this sample of 200 chips. So notice that we could reword this question as, would it be unusual for the proportion of the sample to be less than 0.075? So if you have a problem that involves a sample and then it involves proportions, then that makes you believe that this is a problem involving the p-hat distribution, our distribution of sample proportions. Now remember, technically, in order for this distribution to be approximately normal, we need n times p to be at least 10, as well as n times 1 minus p to be at least 10. But I think we could do a quick check here. We just need to know what n is and what p is. But n is our sample size, and we can see that that sample size is 200, and p is the true population proportion of chips that are defective. But if you go back to the beginning of this question, they give us that information. They say that for a certain chip, the true proportion of chips that are defective is 0.1. So if you did n times p, 200 times 0.1 would give you 20, and if you did 200 times 1 minus p, that would give you 200 times 0.9. Both of those are going to give you numbers that are above 10. So we can assume that the p-hat distribution is approximately normal, and then we can answer our question. Now remember, in this distribution, the mean of this distribution is p, and p is equal to 0.10. So let me fix that real quick. So we'll say p is equal to 0.10. And we're looking for the proportion of chips that is less than 0.075. So 0.075 would be on this side, 0.075, and I'm looking for this area in here. And so this is back to an area or a probability problem, and so we know that we're going to use normal CDF. And when we use normal CDF, we always need our lower bound, our upper bound, and then our mean and our standard deviation. And in this example, the lower bound is, since it's going all the way to the left, it's going to be negative 10 raised to the 99th power. The upper bound is going to be 0.075. The mean is 0.10. And the standard deviation, you might need to refer to your formulas. The standard deviation of the p-hat distribution is equal to the root of p times 1 minus p divided by n. So if I write that here, I say the root of 0.1 times 1 minus 0.1 divided by my sample size of 200. So let's plug this into the calculator and see what we get. We should get an answer that's definitely less than 50%, but let's see. So we say second vars, normal CDF, lower bound we said was negative 10 raised to the 99th. Upper bound is 0.075. The mean is 0.1, and the standard deviation is, let's see if we can do this all at once, the square root of 0.1, then I say parentheses, 1 minus 0.1, close those parentheses, and then say divided by the sample size. And I could leave it just like that, paste it in, so you can see it's all underneath that square root, and then I press enter. And so there you go, you get 0.1193. So our answer to this question, 0.1193. Okay, let's go down to this last example. So a fish hatchery raises trout to stock streams and lakes. The weights in ounces of a sample of 18 trout at their time of release are given. Construct a normal quantile plot and explain how the plot shows whether it is appropriate to treat this sample as coming from an approximately normal population. So I'm going to begin by just plugging that data into the calculator. So say, I guess we don't have to say second, let's just say stat edit. We've done this before. You say stat edit and plug your data in, and I'm going to clear this list while I'm at it, so I press clear enter. 9.9, 8.6. Bear with me while I just enter the data. Hopefully you're following along with me as I'm plugging this in. Whoops, that was supposed to be 7.8. And then we have 11.4, 10.8, 9.0, 8.4, 10.1, 9.6, 8.2, 9.9, 8.9, 8.4, 9.9 again, 9.0, 10.5, and the last point, 9.1. It's always good to also double check your numbers, make sure you didn't make a mistake, missing a decimal point or something like that. I think we're okay there. So we're going to say second y equals now. Make sure that stat plot is on. So second y equals, stat plot's on. You select the normal quantile plot, so select that last picture. And then after we do that, oh, that's already selected, so you probably don't have to do that right now. After you do that, we say zoom, and then we go to number 9, which is zoom stat. So zoom 9. And there we go. We have a normal quantile plot. It's got a little bit of curvature there, but the way I see it is really just that one point that's kind of throwing this off a little bit. Man, that's a little bit questionable, but I think given what I see here, I would make the assumption that my sample is coming from an approximately normal population. I don't see a number of points deviating from the line. Now, this is not perfectly linear, but at the same time, it rarely is. And so I think that since I don't see an abrupt pattern with a lot of points at the end here, at one of the ends, I think I would say, yes, this is coming from an approximately normal population. Okay, so that gives you a good collection of examples from this module. But before we wrap it up, I just want to remind you one more time of really what I consider to be the biggest ideas in this module. And that is, we've dealt with normal CDF an awful lot. And that's where we're finding the area or the probability related to a normal distribution. And we've also dealt a lot with inverse norm. An inverse norm is the tool that we were using when we wanted to find either a z-score, or maybe we wanted to find a particular value or percentile. So these are the primary tools that we're using, and to go with those tools, we're using 3 types of normal distributions. And so we've seen a normal population. It's really nice when they come right out in a problem and say such and such is normally distributed. And the mean of a normal population is mu, and the standard deviation is sigma. We've also seen the distribution of sample means, the x-bar distribution. And the distribution of sample means is a normal distribution with less variation than a normal population. And the mean of this distribution is also mu, but the standard deviation of this distribution was sigma divided by the square root of the sample size. And then lastly, a distribution of sample proportions, the p-hat distribution. Distribution of sample proportions is approximately normal, and the mean of this distribution is equal to p, which is the true population proportion, and the standard deviation is the root of p times 1 minus p divided by the sample size. That's all inside the square root. Now, remember, in order to for the distribution of sample means and distribution of sample proportions to be approximately normal, we needed conditions. So this one, it was n needed to be at least 30, and in this one, n times p and n times 1 minus p both need to be equal to 10. So let me just correct that real quickly. So we'll say n times p needs to be at least 10, as well as n times 1 minus p needs to be at least 10. So use this as a framework for doing a lot of your work in this module. Ask yourself, is it normal CDF? Is it inverse norm? And then when you're using those tools, especially when you're entering things like means and standard deviations, you need to know what means and standard deviations are you entering? From which one of these distributions are you choosing? So hopefully that summarizes things a little bit for you. And that is everything for Module 7.